decomposition, which is chapter 5. Decomposition. So remember, we always have our dynamical system, topological space, the sigma algebra on it. So if you remember what we have seen like invariant measures. So f star mu equals mu. We also have seen from this invariance, you have a point carrier recurrence, you have a lot of properties. And we have also ergodic measures. Which is, if you have a set that is invariant, so it has to be full or negligible, or 1, okay? And the way to think of this property is like, is about like not being able to decompose your dynamical system into two dynamical systems, okay? Like irreducibility, if you want to use another vocabulary. So E, F, take this guy to this guy, and E complement, F also take this guy to this guy. If you have this, ergodicity is against this. So if this happens, and ergodic, that means that one of these two dynamical systems is negligible, okay? So this ergodic decomposition is about, having an invariant measure. Now, can you decompose this measure into bits that are ergodic, okay? So another thing which is important here, which I discussed last time about, transitivity versus ergodicity. So usually people will some people, they make confusion between these two properties, because if you look at this picture, you might think that if you have transitive meaning that you have a dense orbit, an orbit that goes everywhere topologically, it should imply ergodicity, but that's not the case. There are counterexamples. And also ergodicity doesn't imply transitivity, but it implies, so remember we seen that, under some reasonable assumption on your space, ergodicity imply that F restricted to the support of the measure is transitive. Like you have a dense orbit, like it is transitive in a measure theoretic sense, okay? That's what it means here. And yeah, so today's lecture, so we will go to something stronger, which is minimality. And we will compare that.
Elaborate what sort of transitivity means here.
Yeah, by transitivity, I just mean that there exists a dense orbit, like there exists a point x naught such that f and x naught in the topological sense.
Do we have some topology?
Yes. I assume always that I have a topological space here. Yes, M is a topological space, and this sigma algebra is the borel, the one you get from the topology. Yes, I have all the structure. Yes. So today we will go to something stronger, which is minimality. Minimality, it means that every orbit is dense, like the so-called rotations. And yeah, so let me just say a little bit about ergodic decomposition. So what is this decomposition about? So first of all, you need to know how, like, disintegration of measures. So a way to think of this property is just like, Fibonacci theorem. So you can suppose that you have your space M is a 2 torus, okay? And you have a dynamical system here. You can think of having a set. So we have a Lebesgue measure here. M is Lebesgue. Okay. So if you fix a set, E is a set in the torus. So you can you can write a disintegration of a space into horizontal and vertical. Okay, you can have vertical lines here. So this is S1. This is a copy of the circle. This also is S1. Okay. So the measure of this set with respect to Lebesgue, ME, you can write it as, so the integral along E of, you can write the measure on, I will express what this means. E intersect with Ly times D M X, okay? You can suppose that you have two coordinates here, X and Y. To know the measure of this set in terms of Lebesgue, you can just, write the integral of this measure when you go in this circle, and you take the length of this piece. Okay, this is a type of Fibonacci type. So this is what decomposition is. So here you're decomposing with respect to a partition. The partition is just given by the vertical lines. Okay, so we need to formalize this. Okay, this is what we need to formalize here in this. So we will do a disintegration with respect to a partition. So it's good to have this projection. So let P be a partition of M. So you can define this projection. So think of partition. You have in this example, the partition. An example of partition is just these vertical lines, these circles. Okay, pi, which is from M to P. So this guy, pi of x equals px. Px is the element of P that contains x. Okay, so px is the element. Think of these partition element, in some cases to be like a foliation. You have a foliation of your space in terms of lines or two-dimensional objects, or is an element of P that contains x. So if this partition was also a measurable partition, you can, this will be well defined because almost every point will belong to just one. Okay, almost every point will just belong to one partition element. Okay, so to formalize this definition, you need now to put a type of sigma algebra on this object, on the the elements, the sets that are like union of partition elements. Okay, so we need to define the sigma algebra definition. So the sigma algebra B hat on P is defined so that this guy is measurable, so that pi is measurable. Okay? So that pi is measurable. Okay? This is a most natural way to define. This means that measurable sets here are pre-images of elements of P. So measurable sets of P hat are like pi minus 1 of P hat. P hat is just a union, can be a union of these guys, okay? Sorry, measurable set. Here, measurable sets. So let me, measurable sets of measurable sets B hat or Q hat. So this is the notation of this sigma algebra R, such that pi minus 1 of B hat, Q hat, sorry, is in B. Okay. So you can define now, when you have measurable set, you can define a measure definition. So all these is just to formalize this type of Fibonacci results in general definition. So the measure mu hat on B hat is defined by, so naturally the measure of mu hat of Q hat is just mu of B minus 1 of Q hat. Okay? Okay, so you have a type of identification between the two sigma algebra, so, and you define the measure using this identification. So now let's define this disintegration definition. So I have my measure mu, I have my space M, I have a partition. So, okay, suppose that mu is given, mu and P are given. Okay, we have a partition. So a disintegration of mu with respect to P is a family of measures mu P, where P is in P. So in each partition element, you want to define a measure. Just like here, along each of these lines, circles, you have your Lebesgue measure, which is just the length. Okay? So in each partition element, you have a measure with the property that, you know, probability mu P of each of them gives of P is 1. It's supported on that guy, on that partition element for mu hat almost every P in P. Okay. And that it should be measurable at least. So for every E, like the way the measure is changing along in this transversal direction is changing in a measurable way. Here, everything is nice, it's changing smoothly, okay? So for every E in B, the map P gives mu PE is measurable. Okay, so this is a natural assumption to put. Okay, because you just cannot, you know, choose anyhow this measure, like, you know. So some crazy way to choose it, you said, here I'm putting Lebesgue measure, here I'm putting Dirac delta of a point. So that's going to destroy this condition. Like you say here I have Lebesgue on this leaf. On a nearby leaf I have like Lebesgues or Lebesgues everywhere except one guy. It's difficult to destroy measurability, but this type of example will mess up your decomposition. So we don't allow that. We want these changes to be measurable. And the most important part is this now. Well, they are equally important, these properties. The measure of a set, you can recover the measure of a set via this decomposition. It's just mu PE d mu hat P. So if you just take any set, you measure you take the integral when you go along your partition elements, okay? This way. So an example. Let's say you have a finite partition. Finite partition, so P equals P1, Pn. So I just have finite guys. So you can define B hat of this guy, Pi, equals mu of Pi, okay, naturally. And then mu Pi of E is, so you take, this is mu I of E, and this is just, you look at the conditional measure. Pi. So if you're familiar with probability, this is just the conditional measures. Okay. So, by the way, not every partition and measure have a disintegration. Okay. So there is this exercise actually. I want you to do this. I think it's not in the book. So if you take the circle rotation r theta, so irrational circle rotation. You take the partition P that is given by r n theta of point x, where x, so n is bigger than 1. So Lebesgue measure doesn't have a, show that, try to do these exercises, maybe on Friday with Matteo, show that Lebesgue does not have disintegration with respect to P. So you will use the fact that Lebesgue is invariant, okay? Disintegration doesn't have disintegration with respect, and this is irrational. You know, every orbit is dense with respect to P. All right, so there's another property of, so I'm just going a little bit fast because this is, I'm just, you know, telling you the results about this disintegration, and we go to unique ergodicity. So there is the property that the disintegration is unique, you know, because, you know, it doesn't make sense to make a definition, you know, and then you would have to make a choice when you want to apply this. So there is this proposition. If assume that B has countable, so this is using an assumption, B, which is reasonable, has a countable generator. Gamma, like, you know, you have this gamma that generates B and it is countable. You have it when you are on some reasonable topological space. So if mu P and mu P prime, so I have a partition, okay? I did not say it, but I suppose we have a partition. Our disintegration of mu. So if you have these two guys of mu with respect to P, okay? With respect to P, with respect to the same partition, then these two are equal. Then mu P equals mu prime P for mu hat almost every P. Okay, so let's try to prove this. So the proof is not difficult, it's just short. So you take the algebra generated by this gamma. By gamma. Now you can try to see what is the mu hat measure of the difference between these two guys. Like you can define these two sets. So given A, which is in this algebra, this will be countable. You define QA to be the set of P in P such that mu P of A is bigger than mu prime, mu P prime, of A, and RA to be the set of P such that mu P A is strictly less than mu P prime of A. So the aim is to prove that this has zero mu hat measure. Okay, the aim is to prove this has zero mu hat measure. So you have a disintegration. So by definition, this property, this third property here, so you have that mu of A intersect with Q minus 1, P minus 1 of QA. So this is integral mu P, but just by definition, of A intersect is P minus 1 QA. Give me hat P. Okay. So this this is over P. Okay. I like the union of guys. So you can write this as the integral when you are in Q of P minus 1 dB hat P. Plus, when you are in the complement, QA, okay, I did not. PA intersect. Yes, so this is the same. Okay. And here you can see that this guy will be 0 here. This guy will be 0 because when you are in the complement, you will have that this measure is 0, okay? Because so if P is in QA, then P is a subset of P minus 1 of QA. So these are sets in the sigma algebra. These are measurable sets. So P is inside there, and mu hat. So this mu P of P equals 1. We have this property by disintegration here. So what you would have is that if P is here, you would have that this guy is 0. So P is in QCA. This implies that P intersect 0. Okay? So what you have is now mu.
How are the sets QA and RA measurable?
That's a good question. Well, that's a good question.
I think we should somehow use the second property, but I don't use
Yes. Yeah. That's a good question. Yeah. Yeah, you can write it as. Yeah.
I see, yes.
Yeah, yeah. Mm-hmm. Thank you. That's a good point. And you can see that this is just the integral along QA of mu prime. Similarly, d mu hat. And this will give you that this guy has zero measure. And similarly for RA, okay? So, yeah, I am speeding a little bit because I realize that we are very slow in this. So here is the Rochlin disintegration theorem. So disintegration. The proof is a little bit long, very involved. So if you assume that M is complete metric space, and P is measurable partition, then mu admits disintegration. So under reasonable assumptions, so I have mu, mu admits a disintegration. Respect to P. To P. So I should say maybe how are these used in dynamics, for instance, like the Rochlin disintegration theorem. If you remember from the previous lecture, I was explaining the Hopf argument, for instance, which is proving ergodicity for hyperbolic systems. If you remember, I had a type of, I was disintegrating the measure in terms of this stable and unstable manifold. So, so that is something you can do using, by this theorem, you can always assume you have that. And there are many other places where you can do it. So this theorem doesn't use any, property like invariance, for instance. You see that I'm not assuming that this measure is invariant, okay? Now there is another theorem which is more interesting for us. So that if M is complete separable metric space, M complete separable metric space, and F is measurable. Okay, this was an assumption we always have. F is measurable. And mu is F invariant. Yeah, so then there exists we have M0, a subset of M, which has full measure. So I'm always supposing that I have probability measures. and a partition P. So this is a partition of M such that mu has disintegration with respect to P. And not only we have a disintegration, but now we have a disintegration into ergodic measures, okay? So mu P, moreover, mu P is ergodic, is invariant and ergodic. For mu hat almost every P. Okay. Yeah, I can sketch maybe the proof of this one. Yeah, so let me.
M0 in the conclusion of this thing.
How do we?
We define M0
Yes.
and never use it.
Well, it is a partition of M0. Yeah. Yes. Sorry. Yes. Sorry. Yeah. You know, the way the sketch of the proof so we have all these nice properties, separable metric space, so we can just suppose that we are on a countable algebra. So let A be countable algebra that generates B, okay? So for every A in the algebra, you can define this set MA is a set of points where you have convergence of these time averages. So X in M. So it's a tau X A exist. Remember, this was just the tau XA exists, meaning that this limit exists, the limit when n goes to infinity, 1 over n, or 1 over n times the cardinality of j between 0 and n minus 1, so that fjx is in A. Yeah, the frequencies of visits, yeah. So by Birkhoff, implied that this set has full measure because mu is invariant, okay? This is why you use invariance here. Mu of MA equals 1. Okay? So what you define now, you define M0 as the intersection of these guys. A in A, This is a countable intersection, so this guy will still have measure 0. Meso 1, sorry. I'm saying 0, the opposite of what I want to say. And now you need to define a partition. So the term tells you that there is M0, there is a partition. So the partition will be defined by equivalence classes, okay? So you say that X is in relation with Y if and only if these guys are the same. Tau A X equals tau A Y. For every A in A. So you can check that this, so the partition are given by equivalence classes. So P given by equivalence classes. You can check that this is a measurable partition, like these guys are measurable by sequences, okay? Yes. Yeah, I was saying I will sketch, but now I'm doing the whole proof. Okay, no problem. Well, I will ask you to check the proof in the book because I did not plan to do all this for this chapter. So you can continue the proof here, okay? The way you do it here is you will, to prove that this partition is measurable, you need to find these sequences of points where, you know, if you have two different partition elements where this guy is bigger than this, you can find a sequence that is converging, and you can take this partition as refinement. You know, this partition will be given by limits of partitions, okay? So you can find the proof in the book. So this is what I wanted to say briefly on this chapter.
Professor, can I ask a question?
Yes.
You stated that when you use this like disintegration of measures to prove the top argument in the general case.
Mm-hmm.
Well, I don't know how to do it. My question is, the general case when you need to prove that the Jacobian of the Poincaré transformation are C1, maybe Lipschitz, I guess. They absolutely constitute.
Yeah, you don't need C1. You just need Holder continuous will be okay. Yes.
But we need to use this integration.
Yes, you need to disintegrate your measure into the stable and unstable leaves. For that, you can see that this equivalence relationship, the equivalence classes are exactly the stable leaves. Because these points, they will have the same feature if they belong to the same stable. Actually, this partition that is constructed here will be the partition given by stable leaves when you are on a hyperbolic system. Because if you see that if you are on the same stable, we did this proof when we were explaining Hopf argument. So if you are on the same stable, you have the same, feature. The frequency of visits are the same. And yeah. Yeah, so you talk about something important which we did not prove, and we don't have the arguments to prove it, which is the absolute continuity of these foliations. But that's not something we can do in this course, unfortunately. So we will talk about unique ergodicity. So in the previous lecture last week, we talked about ergodicity and transitivity, and here we will talk about ergodicity versus minimality. Okay, minimality, I will define what it means. So definition. F is measure. So I always talk about probability measure. So B, which is F, admits a unique ergodic measure. Again, for this course, when I talk about ergodicity, I suppose that I have invent measure, okay? Unless otherwise. Ergodic measure. So clearly, this implies this. C, A implies B, because when I talk about ergodicity, I mean invariant already. So this is important that you have conversions for every observable continuous. We have 1 over n. This will, I equals 0, n minus 1, a phi composed with fix is converging. This guy converges. This guy converges for all x. This is stronger than Birkhoff ergodicity because it was just with respect to a measure. But here we have only one invent measure, so we have it for all B. D, sorry. For every phi C0 M, this convergence is uniform. 1 over n equals 0 converges uniformly. Okay. So you see how strong unique ergodicity is because of these two properties. So we have Birkhoff for every point. Yeah, the proof. Yeah, this implies this is easy. And also, this guy implied this is also simple. So let's check B. Yeah, if you have a unique ergodic measure, sorry? B implies, yes. Yeah, B, no, I'm not proving, oh no, so what I'm saying. C implies B, that's what I want to prove, sorry. C implies B, yes. Yes. Yeah, I was just commenting that this is easy from B to A because you can use the decomposition theorem to produce two measures, okay? So you want to prove, you suppose now that you have two ergodic measures, so yeah, it is also easy, I think. This is also simple. Right? If you have let mu be ergodic, by this property, you have that it is converging to, for every point you have convergence. And also use Birkhoff, so this is converging to phi d mu, this is also converging to phi d nu. Okay? And we know that this is, if you do not have unique ergodicity, you might say that the two sets where you have convergence are different, but here we have it, you have convergence pointwise everywhere. So these two are equal, and this is equivalent to mu equals mu. Yeah, this is also simple. Yeah, and A implies D. I think this is, yeah, A implies D is a little bit more. You have this, A implies, yeah. So A, because this is easy, D implies C is also simple, okay? A implies D. A implies D. Or let's prove that not D, so implies not A. So suppose that we have the exist C that is C0, and for which
If the previous one, Ergódica tells us that this is convergence almost everywhere.
for respect to the measure mu, yes.
And we know that the series converges for all x.
Yes.
But why does it converge to exactly this thing for all x?
Yeah, because for almost, because we know that there is at least one x that it converges to this one, because Birkhoff tells us that there is one x for which it converges to this one.
Yes. Does the third condition mean that it always converges to the same value?
Sorry? Yeah, it is in the previous chapter.
Maybe, but I don't understand where do we even use the third condition here?
You mean this condition?
Yes, we want to prove that C implies B. Where do we use C?
So there is ergodicity that tells us that this is converging to a constant almost everywhere.
Yes.
To a constant almost everywhere.
Yes.
Okay? But this is telling me that it's converging at every point you have this convergence.
Yes.
Is this not clear? Or I'm missing something?
And what next?
Sorry?
And what next? Yes, I understand what you have said, but
But so what I mean is these two, they have to be the same, these two limits. Is this not clear? I'm saying so.
So it does not depend on the measure. The limit has to be the integral with respect to the Ergódica measures, and they are two Ergódica.
Yes.
Ergódica measures.
So yeah, you
well, okay then. Disregard. I'll ask after.
okay. Well, you can see that. Okay, let's. Okay, so it's good to to have these discussions sometimes. So there is Birkhoff. Just from invariance, you have that this is converging. To n minus 1 phi composed with fi x. This guy is converging to phi tilde x. This is just Birkhoff from invariance. Now ergodicity is telling you that this is constant and is the integral of this function.
But the convergence is
Respect to measure, yes.
yes, it is with respect to measure.
Yeah. Yeah, yeah, so this function will be invariant under f, so it has to be constant.
Yes. Almost everywhere. Mu almost everywhere.
Yes.
And the same thing to the second measure.
Yeah, but to whatever is converging, that guy has to be invariant.
Yes.
That guy has to be invariant. And invariant functions are constant. This guy has to be invariant by f. Maybe we have this discussion after, yeah? Yes, okay. So suppose that you have a so, yeah. So in particular,
Yeah, this makes much more sense.
does not converge. You don't have uniform yeah. So what did I say? So I pick a. I'm proving A implies D, not D implies not A. So if you don't have convergence, so I take an invariant measure. Okay, I can have one. I mean, supposing that my space is reasonable. Okay, this mu is an invariant measure. And from here, you want to construct another invariant measure. So mu is an invariant measure, okay, by existence theorem, okay. Mu is invariant, given by existence. So if you don't have uniform convergence, that means that for every epsilon positive, there exists k and nk bigger than 1, xk plus sequence of points where 1 over nk minus 1 of xk. This guy is bigger than epsilon. And you define this measure nu k as 1 over nk, the sum so up to going to a subsequence, because the unit, the space of probability measure is weak star compact, so up to subsequence, this guy converges, okay? We have nu k is converging weak star to some measure, let's say nu, okay? Now the claim is nu is different from mu. So to check that two measures are different, you just have to check that there is a function for which their integrals are different. So, and we have a good candidate, the function we started with. So the integral of phi d nu is the limit when k goes to infinity by the definition of this convergence. The integral of phi d nu k, okay? Which is limit when n goes to infinity of 1 over nk, the sum phi compose fi xk. And we know this is bounded away from this guy by epsilon. Is is bigger than epsilon by this. Yeah, I was telling about, okay, we have half an hour to discuss minimality and ergodicity. So on Wednesday, I will give exercises about this part. Yeah. So let's talk about minimality. So, definition. So let lambda compact invariant. So invariant is by this, I just mean f of lambda is inside lambda. So lambda is minimal if you have that fnx for all x in lambda. Like every point is dense. Every orbit is dense, sorry. So for this, there are many examples in dynamical system for minimal guys. One is the irrational circle rotation. So our theta is irrational. And you can also have a flow on the torus with irrational slope. So you can think of this guy where theta is irrational. Every orbit will be dense. And so there is another example which is more sophisticated, which is the horocycle flow. This is the flow given by the stable manifolds of the geodesic flow in negative curvature. So yeah, you don't need to know this, but if you know it, this is minimal. The horocycle flow is the flow whose orbits are the stable manifolds of geodesic flow in negative curvature. Negative curvature. I'm talking about surface, okay? Because otherwise this is higher dimensional, okay? Yes, at the end I want to sketch an example, which is, so if you remember, we proved that ergodicity implies transitivity on the support. Here also we have minimality proposition. So suppose that F is uniquely ergodic. So it has a unique invariant measure. So then F restricted to this, restricted to the support of this unique invariant measure is ergodic. So let me be the unique event measure. And let's write lambda to be the support of mu. So the support is compact and it is invariant. I think, did I give that? I don't remember. But yeah, if the measure is invariant, the support is also invariant set. So if you support, so we want to prove that every orbit is dense here. So we want to look at this dynamics. Okay, we want to prove that every orbit is dense. So we suppose that we don't have, there's an orbit, there's a point where the orbit is not dense, and we construct another invariant measure different from mu. So suppose that there exists x naught such that x naught in lambda such that this guy is not dense. It's a subset but not equal. So that means that for every, this means that there exists U open set such that U intersect with the support is not empty, is lambda empty. And F J X naught is not in U intersect with the support, is lambda for all J. Okay. So yep. So you define this measure nu of n along this orbit. So clearly, nu n of U equals to 0 because these points are not in U. And so you can take a limit. So when I say limit, think of going to a subsequence, okay? A weak start limit of this guy. And this will be an invariant measure. Okay? We know how to check this. And this is equivalent to saying that the integral of phi d nu equals is converging nu k nu n phi d nu. So U intersect with support with lambda, sorry, I should have used support, is not empty. This implies that mu of U is not 0. But nu of U is just 0, okay? So for the 15 minutes that we have left, I want to give an example like this, is it Furstenberg theorem that gives an example of a system that is minimal but not ergodic. Okay? This theorem by Furstenberg. So there exists a real analytic diffeomorphism F from T2 to T2 that is minimal, preserves Lebesgue, but not ergodic. So that is minimal, preserves Lebesgue, but not uniquely ergodic. It's just to tell you that unique minimality doesn't imply unique ergodicity. Ergodic, okay. So this is just to say unique ergodicity is strictly stronger. Strictly stronger than let me sketch how the construction of this example. Construction of this example. So the construction starts with a system F0 T2 to T2, which is just you take x, y, gives x plus alpha, y. It's just a shear, okay? You changing in the x direction, you keep y, okay? So you suppose that you can choose alpha so that this guy, F0, preserves Lebesgue not minimal and not ergodic. So what you want to do now, you want to perturb this to produce a minimal guy here, okay? So the way to do it is, you want to perturb it. You say, when I perturb, in general, when I perturb a dynamical system, the new system I have is kind of conjugate to the original one, okay? So we are looking for F, that is H composed with F0, composed with H minus 1. So you want this so that H is a map on the torus that preserves Lebesgue, okay? H from T2 to T2. So this H is what we're looking for. Preserves Lebesgue. So to destroy minimal, to get minimal here, this H should not be continuous. You have to destroy the continuity. Because if H was continuous, it will map orbit to orbit. So if the orbit is dense here, it will be dense there. So if you want to construct an example that is minimal, you should destroy continuity of this. And there is a very a way to do this type of perturbation in dynamical system. I'm just going to sketch it here. So, so fact is what I just said. If H is continuous, then F cannot be minimal. So when I say minimal here with respect to the T2, okay, on the whole guy. So now you want to find H. So what you do is you can write the equation that H should satisfy. I can add more condition to say I'm looking for a function f x y that I'm not changing here y plus, here I add a function that depends on x. This is something very much used in dynamical system to perturb this, to destroy certain properties like minimality or to get minimality. Okay. So you say this is the function that I'm looking for of this form. Okay, this is how constructed this example. So what is the equation for H now? So F composed with H, so this is equals H composed with F0, okay? This is what H should satisfy. So that means that F of H1 xy, H2 xy, this guy will be what? This is H1 xy, by this is what I'm looking for, plus alpha. And then y, which is H2 xy plus phi of H1, okay? So this is a comma. You have these two coordinates. Okay, so this is telling you that H1 of x should be H1 of xy. Like you write what this is, okay, using the definition of F0. So H1 of xy has to be x, and H2 of xy is y plus a function u of x here, where u of x plus alpha minus u of x equals phi x. Okay? Now you're looking for your function u that satisfies this property. If you have u, you have h, and then you have your guy here. And this is a well-known equation, which is a cohomological equation, which is of this form: u composed with r alpha. R alpha is the rotation, minus u equals phi. And this, so this is a cohomological equation. And the solution, solving this equation, will give you f. And we don't have tools, but there are ways to solve this equation using limits. And but just for this course, so if somebody is interested, it can be a presentation at the end of this course. So the solution of this equation will give this property here, that you keep not ergodicity, but you make it minimal, okay? So I think I will stop here for today, and I will see you on Wednesday.